Hello everyone and welcome to lesson 29. Today we're going to be starting section 3.1. This is going to be our first day where we're focusing really on increasing and decreasing. Okay, so we want to get started today just by recalling what we already know about increasing and decreasing functions. And from what we reviewed in that introduction activity yesterday, hopefully we remember that when we're talking about increasing and decreasing, we're going to be using interval notation. And we list those intervals using our x values. So just as a quick reminder, let's go ahead and actually define increasing and decreasing. So formally, a function f is increasing on an interval when for any two numbers x1 and x2 in the interval, when x1 is less than x2, then our function evaluated at x1, so f of x1 is less than f of x2. So as your x values are increasing, your y values are also increasing. And then contrastingly, a function is decreasing if on an interval x1 and x2, when x1 is less than x2, your function is decreasing or your y values are getting smaller. So something we want to recognize as we move forward with this section is that we can use calculus to help us determine intervals of increasing and decreasing for a given function. So we want to recognize that the derivative, which remember is also the slope of a tangent line, can be used to determine if a function is increasing or decreasing over a given interval. So before we jump in, we're going to look at one quick overview example. So we want to think about a very well-known function. Let's think about f of x equals x squared and what that looks like. Hopefully you have a picture in your head of our parent function parabola. So what we know already, what we reviewed before in our introduction activity, is that we can already define where this function is increasing and decreasing using our algebra 2 skills. We know that this function is increasing from 0 all the way up to infinity, and this function is decreasing from negative infinity to 0. And with a basic function like x squared, that is fantastic. However, we are going to be looking at some more exciting functions. So we want to be able to use the calculus that we know to answer these types of questions without actually having to analyze the graph. To do that, we want to introduce the derivative, and more specifically, we want to be looking at the slope of the tangent line. So notice everywhere we said our function was increasing, the tangent line at any given point is also positive. Anywhere we said our function was decreasing, the tangent line was negative or has that negative slope. And then right there in the middle, we have that horizontal tangent. So what we can actually do is we can take our function f of x equals x squared and we can take the derivative. So if we have f of x equals x squared, then the derivative f prime of x is just equal to 2x, and then we can actually find where we're going to have that horizontal tangent, a question you guys have done a ton already. Find where we have a horizontal tangent. We take our derivative 2x and we set it equal to 0. Dividing by 2, we get x equals 0, and this is what's going to be called a critical number. And we will define that in just a minute. From there, we know that's where we're going to have that horizontal, so we want to investigate what's happening around it. So we're investigating the sign of our derivative to determine if the slope of the tangent line would be positive or negative. And if we plug any value in on the right side of this number line, any positive number into our derivative, we're going to get a positive value. And if we plug any negative value into our f prime of x, we're going to get a negative value. So we know that this confirms that our function would be increasing from 0 to infinity and decreasing from negative infinity to 0. So just a really brief overview of what we're going to be doing with the derivative in this section. So now we just want to take everything we just previewed and sort of formalize it. So here we have, it says test for increasing and decreasing functions. Let f be differentiable on the open interval from a to b. So notice today we are only going to be talking about an open interval. Then you have your 1, 2, 3 rules that we can use to test for increasing and decreasing. Something we just want to take note of is that for all of these, we are going to be testing values in f prime of x, the derivative, but then we're going to be stating increasing and decreasing about our original function, so about that function f of x. So just like we did in the first slide, we were using our derivative to answer about our original function. So we're going to be plugging into the derivative, but answering questions about our original function. So the 3 rules: if f prime of x is greater than 0, for all x in your open interval from a to b, then your function f is increasing on a to b. So that means you plugged a value into the derivative, you got out a positive value, so you know your original function is increasing. If f prime of x is less than 0, so you plug a value into the derivative and you get out a negative value, then your original function f is decreasing. And then finally, if you plug a value in to your derivative and you get out 0, then your original function is constant, and that there's no sign for that. Okay, so then looking at the next section, it says a function is increasing when, as x moves to the right, its graph moves up, and is decreasing when its graph moves down. So we're going to be filling in these 3 blanks about this picture on the right. So remember, the derivative is related to the slope of a function. So for example, the function that's given here is decreasing. Thinking about the slope of our tangent line on this first interval, which would go from negative infinity all the way up until x equals a. And notice that our f prime of x is less than 0 on those intervals. The slope of the tangent line is negative. The function is constant, meaning the slope of the tangent line is equal to 0 in this middle interval between a and b. And then finally, the slope of our tangent line is positive on this third interval. So our function is increasing from b all the way to infinity. And remember, with increasing and decreasing, it's always going to be parentheses in our intervals. Okay, so a quick 3-step process for how we're going to determine increasing and decreasing for a function f of x. So step 1, we're going to find our derivative. Find f prime of x. Then step 2, what we need to look for are those critical numbers. So we're going to find our critical numbers. And so I have here for you the actual definition of a critical number. A critical number says let f be defined at c if f prime of x is equal to 0, so you have your horizontal tangent, or if f is not differentiable at c, then c is a critical number. So what that means are there are actually 3 types of ways to have a critical number. The first would be at a vertical asymptote. The second would be at a vertical tangent. or at a cusp. So those are the three ways that you would see f not differentiable at c, or of course your f prime of x is equal to 0. So you're finding your derivative, then you are finding your critical numbers by locating your horizontal tangent, setting equal to 0, or looking for one of these three cases. Then finally, we're going to test our critical numbers in our derivative in f prime of x. We're going to check out those signs to determine increasing or decreasing. All right, here we go. Let's jump in with an example. So here we want to find our open intervals for which our function f is increasing or decreasing. And we're going to start out with the function f of x equals x cubed minus 3/2 x squared. So following the three steps that we did, that we listed in our last slide, step 1, we're going to actually find our derivative f prime of x. And that is a skill that we certainly have by now. So using our power rule to start, we get 3x squared minus bringing our 2 down, 2 cancels, we're just left with 3x. So there's our derivative. Now number 2, we want to actually find our critical numbers, which remember happen at any horizontal tangent, so where f prime of x equals 0, or anywhere where our function is not differentiable, so at a vertical asymptote or a vertical tangent or a cusp, and we can see that we don't have any of those in this case. So we just need to look for where our derivative f prime of x is equal to 0. So taking that derivative that we found, 3x squared minus 3x equals 0. Factoring out that 3x, we get 3x times x minus 1 equals 0, and we get critical numbers at x equals 0 and x equals 1. So then finally, our last step, step number 3, is to test our critical numbers in our derivative f prime of x. So to do this, I'm actually going to set up a number line, and I'm going to put my two critical numbers on there, 0 and 1. And then I'm going to choose a value to test in each interval. And I can choose anything I want, so I'm going to try to make it as easy as I can on myself. And when I test, I'm testing inside f prime. So let's do something like, I don't know, -2, 1/2, 2. You can plug in anything you want. It's important to note that you're plugging it into f prime. So if we look at f prime of -2, we would get 3 times -2 squared minus 3 times -2. -2 squared is 4 times 3 is 12. Minus is a plus 6. Gives us 18, which is a positive value. We also want to plug in 1/2, again, into our derivative. F prime of 1/2 gives us 3 times 1/2 squared minus 3 times 1/2. 3 times 1/4 would be 3/4 minus 3/2 is 3/4 minus 6/2 is negative, 6/4, there we go, is -3/4, which is a negative value. And then finally plugging in our last interval there, f prime of 2. Now again, I just chose -2, 1/2, and 2. You can pick anything you want. As long as you plug it into that derivative, we would get 3 times 2 squared minus 3 times 2. 3 times 2 squared gives us 12 minus 6 is 6, still a positive number. Once we've done all of that, we can go ahead and list out our intervals. So remember, our function f of x will be increasing anywhere that our derivative was positive. So that would be on the interval, the first and last on our number line. So from -infinity to 0, and from 1 to infinity. and our function f of x is decreasing in that middle section there from 0 to 1. So just notice we used our derivative to do all of that. Not once did we look at the graph. We can, however, use the graph to confirm that we are in fact increasing from negative infinity all the way up till 0, and then again from 1 to infinity, and then we are decreasing between 0 and 1. Okay, so another example here, we want to determine intervals where our function f is increasing or decreasing with the given function f of x equals x cubed minus 3x squared plus 3x. Following those same three steps, we're going to first find our derivative f prime of x. Using the power rule, f prime of x is equal to 3x squared minus 2 times 3 is 6x plus 3. Our next step would be to go ahead and actually find any critical numbers, which we do by setting our derivative equal to 0 or evaluating any places where our function is not differentiable, so vertical asymptote, vertical tangent, or a cusp. Again, we don't have any issues here, so we just need to look for our zeros. So taking this derivative, 3x squared minus 6x plus 3 equal to 0, I'm going to factor out that 3. I'm left with x squared minus 2x plus 1 equals 0. We can go ahead and factor x minus 1 and x minus 1 gives us a critical number just at x equals 1. Once we determine that critical number, our final step is to actually test those critical numbers in our derivative. So I'm going to set up a number line. Now I only need my one critical number on my number line, and I'm going to test around it. So again, you can choose anything you want. Easiest for me to test something like 0 and maybe even 2. Remember, we are testing in that derivative, so f prime of 0. Now looking at my original derivative here, this would be 3 times 0 squared minus 6 times 0 plus 3 gives me 0 minus 0 plus 3 is just 3, which is a positive number. And then I want to evaluate at 2. So f prime of 2 is equal to 3 times 2 squared minus 6 times 2 plus 3 gives me 3 times 4 is 12 minus 12 plus 3 is also 3, which is also a positive number. So you always want to make sure to actually test all of your intervals and to not just assume it's going to alternate. From here, we want to go ahead and determine any intervals of increasing and decreasing. Notice we got two positives, or we got a positive in each of our intervals, which means our function f of x is increasing. On our first interval from negative infinity to 1, and then again from 1 to infinity. But because 1 was that critical number, remember we actually have that horizontal tangent at 1, so we want to be sure not to include it. And then again, we did all of this using calculus and the equations. We didn't look at the graph at all, but just to confirm, we can always check it out. Looking at our graph, we are increasing, increasing, increasing all the way up, and then at 1 we have that horizontal tangent, but then we continue on increasing. Okay, moving into our third of 4 examples today, and yes, this one looks a lot more exciting. Again, just going to find the open interval where our function f is either increasing or decreasing, but here we have our function f of x equals the quantity x squared minus 4 all raised to the 2/3 power. Same 3 steps, we're going to start by finding our derivative, f prime of x. And I can feel you getting excited because in order to find f prime of x, we get to bring back the chain rule. So here we have that inside function, x squared minus 4, and that outside function, something to the 2/3 power. Remember, using the chain rule, you bring your power in front, keep the inside the same, make your power 1 less, so 2/3 minus 3/3 gives you that negative 1/3. And then chain rule, so times the derivative of the inside, so the derivative of x squared minus 4 is just 2x. Wow, what a throwback. Simplifying our f prime of x, notice we have that negative exponent, which means we're going to have to create a denominator. In our numerator, we're going to be left with the 2 times 2x gives us 4x, and our denominator is going to have 3 times, and then our quantity x squared minus 4 to the 1/3 power. So we're using the chain rule just as our first step in this problem. Once we find our derivative, now we want to find our critical numbers. So remember, we're looking for our critical numbers, meaning anywhere that our function or that our derivative is equal to 0, so f prime of x equal to 0, but also at any of those other issues like the vertical asymptote or the cusp or the vertical tangent, anywhere that it's not differentiable. And because we have a denominator here, we're going to actually have to investigate some of those as well. So let's start by taking our f prime of x and setting it equal to 0, which I can do by setting my numerator equal to 0. So we get x equals 0 as a critical number. We also want to look at any problems we might have, so we're going to take our denominator and set our denominator equal to 0 as well. So here we have 3 times x squared minus 4 to the 1/3 equals 0. Dividing by 3, we have x squared minus 4, to the 1/3 equals 0. If we cube both sides, we're left with x squared minus 4 equals 0, so x squared equals 4. So we have critical numbers at x equals plus or minus 2. So this problem is already way more exciting than the first two because we got to start it out by doing the chain rule. Then to investigate for our critical numbers, we had to look at both cases where our derivative equals 0 and also where we have a non-differentiable point. And then we found 3 critical numbers. So for our final step of testing our critical numbers in our derivative, f prime of x, when I create my number line, I have a couple things to add on here. We have to add our -2, our 0, and our 2. And then from there, I'm going to add in the values that I'm going to test. Again, you can add anything inside these intervals. I just tend to try to choose things that are a little bit simpler. Now this derivative is a little bit funky looking. So when I go through, I don't necessarily have to solve each of these all the way down to a final value, as long as I can tell what the final sign is going to be. So let's look at what I mean by that. If we're looking at f prime of -3, looking at my derivative, I would have 4 times -3 over 3 times -3 squared is 9, minus 4 is a positive 5 to the 1/3 power, which gives me -12 over, and in my denominator, whatever the third root of 5 is times 3 is definitely a positive number. So I know 3 third root of 5. I know that a negative divided by a positive is still a negative, and what I'm going to get out here is a negative. It doesn't necessarily matter exactly what the value is. I only really care about this sign. Now that's okay. I don't want to stop too early and jump. Make sure I want to go as far as I need to make sure that I am sure that it's the right sign. Okay, so I'm going to continue going through all of my values. F prime of -1 gives me 4 times -1 over 3 times -1 squared is 1 minus 4 would be the -3 to the 1/3 power, which gives me a -4 over a, remember you can take the third root of a negative because a negative times a negative is a negative, so we would get times the -3 third root of 3. A negative over a negative, though, gives us a positive. Continuing on, f prime of 1, feel free to pause me and go ahead and do these values on your own. F prime of 1 would give us 4 times 1 over 3 times 1 squared is 1 minus 4 is negative 3 to the 1/3. Here we have a positive 4 over negative 3, third root of 3. Positive over a negative gives us a negative. And then finally, f prime of positive 3 gives us 4 times 3 over 3 times 3 squared is 9 minus 4 is 5 to the 1/3 is a positive 12 over a positive 3, third root of 5. Positive over a positive is a positive. Okay, lots of little algebra, lots of room for mistakes, so make sure you guys go slowly through those, especially when you're doing them on your own, and you double check all of your signs. From there, we've identified our intervals, some as positive, some as negative, so we can go ahead and summarize that our function, f of x, is increasing on two intervals between -2 and 0, and then again from 2 to infinity. And then our function f of x is decreasing wherever we got a negative, so between negative infinity and -2, and then again between 0 and 2. And just like in the last couple, we didn't need a graph to determine all of that. We were able to use our derivative, but we can always check with the graph. So here is the graph of this function. Notice you have these two cusps, which we found at x equals 2 and -2. We found earlier when we were finding our critical numbers. And then you also have that horizontal tangent at x equals 0. From there, looking for our intervals of increase from -2 to 0, we are increasing, and then again from 2 to infinity, and then we are decreasing from -infinity to -2, and again from 0 to 2. Isn't it great when it all works out? Okay, our final example today, same instructions, find the open intervals for which f is increasing or decreasing. We want to do those same 3 steps, but looking at the function x to the 4th plus 1 over x squared, in order to take this derivative as it is right now, we would have to introduce the quotient rule. And while yes, the quotient rule can be so much fun to do regularly, we also want to work on simplifying whenever we can before we take the derivative. So looking at this function, notice we only have that one term in the denominator. Sometimes we see this as a heart, which remember we can actually break this up, so we can write our function f of x as x to the 4th over x squared plus 1 over x squared, which means simplifying, we can rewrite our function f of x as x to the 4th over x squared is just x squared plus, and then 1 over x squared, I'm going to write as x to the -2, because this is going to be way easier for me to take my derivative. So yes, the quotient rule would have been a lot of fun, but this I think will be a little bit cleaner. Now that we've simplified, we can go ahead and follow those 3 steps we've been doing all day long. Start by finding our derivative, f prime of x. So taking this derivative, f prime of x, using our power rule, we get 2x, and then bringing down that -2, we would get minus 2x to the 1 less power is -3. Remember, we always want to make sure we're actually taking one away, and we have to be careful with those negative exponents. So now I'm going to rewrite that so I can actually visualize what it is. So I have f prime of x equals 2x minus 2 over x cubed. And then I'm going to actually make this a common denominator just so I can see what I would have gotten with my quotient rule. So I'm going to multiply by x cubed over x cubed and write my f prime of x as 2x to the 4th minus 2 over x cubed. And actually, we can even write this as 2 x to the 4th minus 1 over x cubed. That is our derivative. So a little bit longer. From here, we can go ahead and actually continue on with our next steps. So we now want to find our critical numbers. Just like always, we're going to look for anywhere where our derivative is equal to 0, those horizontal tangents, and then also any problems, any of those vertical asymptotes, vertical tangents, or cusps. Again, because we have a denominator just like we did in the last one, we are going to have to check out for any of those issues. So let's start by taking our numerator and setting that equal to 0. So let's set 2 times x to the 4th minus 1 equals 0. Dividing by 2, we get x to the 4th minus 1 equals 0. I'm going to break that up. X to the 4th I can write as x squared plus 1, x squared minus 1, x squared, equals 0, equals negative 1, doesn't help me right now. X squared equals 1, I get x equals plus or minus 1. And then I'm also going to set my denominator equal to 0, x cubed equals 0 for any of those places where I'm not differentiable, and we just get x equals 0. So our critical numbers are positive 1, negative 1, and 0. And then our final step is going to be to test critical numbers and our derivative f prime of x, setting up a number line. I'm going to plot negative 1, 0, and 1. Choosing values to go in, or that are between them, I'm going to choose negative 2, negative 1/2, positive 1/2, and positive 2. As always, you can choose something that's different. I'm going to just choose those. Plugging in for each of them into my derivative, let's look at f prime of negative 2. And we get 2 times negative 2 to the 4th minus, 2 all over negative 2 cubed. Again, I'm going to just try to look at the signs here. Negative 2 to the 4th is going to be a positive big number times 2 minus 2 is going to give me a positive over. Negative 2 cubed is a negative, which leaves me with a negative in my first interval. Looking at f prime of, let's bring this up top. F prime of 1/2 gives me 2 times 1/2 to the 4th minus 2 all over 1/2 cubed. Thinking about 1/2 to the 4th. Okay, so I'm actually going to reach for my calculator for this. Just typing this in, we would get 2 times 0.5 to the 4th minus 2, and that's going to be divided by 0.5 to the 3rd. So this gives us a negative 15. I apologize, but I totally skipped over f prime of negative 1/2. Plugging this in, again, feel free to pause me and to try this on your own. 2 times negative 1/2 to the 4th minus 2 over negative 1/2 to the 3rd. Grabbing my calculator, I've got 2 times negative 0.5 to the 4th minus 2 divided by negative 0.5 cubed, and that gives me a positive 15. And then finally, f prime of 2, we get 2 times 2 to the 4th minus 2 all over 2 cubed. 2 times 2 to the 4th minus 2 divided by 2 cubed gives us a positive 3.75. So from here we can identify our function is increasing On to intervals between -1 and 0, and again between 1 and infinity. Whoops. And our function f is decreasing on the other two between -infinity and -1 and 0 and 1. And just like with all the others, we will just take a quick look at our graph. Notice we have at x equals 0, we have that vertical asymptote, which we could expect since our denominator would be equal to 0. And then at 1 and -1, we have those horizontal tangents. Notice we are increasing between -1 and 0. We have a positive slope on our tangent line. And then again from 1 to infinity. And we are decreasing from -infinity to -1, and again from 0 to 1. So using the first derivative to help us determine intervals of increasing and decreasing on our original function totally works. Okay, great job with those. I know they get a little tedious towards the end there, but really good job sticking through. Homework 29 is just 3 problems in section 3.1. For each of these, you are just going to be determining intervals of increase and decrease for the function, just like we did in today's lesson. If you have any questions or you need help, feel free to reach out to your teacher.